Hi, so I'm Deepak. I'm a grad student at MIT, and I'm going to give a topic preview on low-power networks. So my objective with the topic preview is the following. I want to make sure that there are at least 3 questions for every talk in the low-power session tomorrow. And the second objective is that if you're still beginning in the low-power networking space, you should be able to appreciate what the papers are about and what are the key contributions and what remains to be done. If you're already an expert in low-power networking, I guess you would do better than this. So when I decided to do this talk, I ran a simple experiment with my cell phone. I put it on my desk and measured its power consumption or its battery status every 15 minutes or so. And I got this graph. So on the x-axis, I plotted time in minutes up to 5 hours. On the y-axis, it was the battery percentage. And as my phone sat on my desk, the battery reduced, of course, and it went from about 100% to about 85%. And then I repeated the same experiment, but with a slightly different setup. I pinged it once every minute. And with that, my battery reduced drastically. It went down to about 40% around the same time. So with just one ping every minute, I could cause a drastic reduction in the battery life of my cell phone. Of course, this is not a rigorous experiment. This is very hand-wavy. But you get the gist. Communication today is very power hungry. So I decided to dig a bit deeper, and I got this slide from Pengyu and Dinesh. And on the x-axis, we plot the different components of a typical sensor or a smartphone. And on the y-axis is the power that they consume in microwatts. So as you can see, most of the digital components like accelerometers, MCUs, RAMs consume less than or around 1 milliwatt of power. But all of the communication components cost a lot more in terms of power. Wi-Fi, for example, can go up to 100 milliwatts. Hopefully, this has convinced you that communication typically is very power hungry. But why do you care, right? Like, I can always go home, charge my cell phone. Why do I care about reducing this cost of communication for devices? Well, there are multiple reasons. And one reason is that as we continue to increase our communication needs, the battery density hasn't improved as much. So over the last 22 years, the battery density has just improved by 3 times. And because of that, it puts like a big load on our devices. Our devices keep getting larger. They have to fit larger batteries. They don't run as long as they used to. But that's not the only problem. The other problem is that not all devices can have these large rechargeable batteries. Think about smart homes. That in your homes, you're going to have tons of sensors. All of these sensors are going to need communication. And if you're going to have these sensors have large batteries, if you want to be recharging them every day, it's not going to work out. There are other applications like smart farms, where you're going to have a lot of sensors lying around in the field. You want to power them. You want to give them communication. Cannot do it if you have to recharge them every day. And same for like oil fields, mining, all of these resource-constrained environments where you want to do very fine-grained sensing with a lot of sensors, but you cannot afford the cost of communication. And finally, there's the case for in-body networks, where the devices that are implanted inside our bodies that need to communicate data outside. So clearly, you cannot make them very large because they have to go through your body streams. And also, because they're implanted in your bodies, you can't afford for them to die in your bodies. They cannot just run out and stop doing what you want them to do. So because we need to solve all these applications, because we don't want our battery sizes to keep increasing all the time, we want to build low-power networks. And this is going to be the topic of my talk today. I'm going to start by discussing the key principles that are involved in designing low-power networks. Then I'm going to talk about one of the most simple and the most prevalent uses of low-power networks called RFID tags. Then I'll talk about Wi-Fi Backscatter, which is implementing low-power networks with Wi-Fi that are compatible with Wi-Fi devices. And finally, I'll talk about human body backscatter. So clearly, this is not an exhaustive list of all topics that are included in low-power networks. I tried to include all topics that are relevant for the session tomorrow, which is the session on low-power networks. So let's start by talking about the basic principles. And the first question that we want to ask is, what makes communication so power hungry? And to understand that, let's take a step back and try to understand how communication works today. So let's say you open your cell phone. You want to send a WhatsApp message called MobiCom 2018 is the best. And you want to send this message through your Wi-Fi router. So in the first step, you'll just convert these things into bits, and then you want to convert these bits into electromagnetic RF wave that will go from your cell phone to the Wi-Fi router. Let's dig a bit deep into how you go from these bits to this RF signal. So first, what you do is you convert these bits into complex numbers. This is a process called modulation. So if there is, for example, the simplest way to do it is to map them to +1 and -1 on the complex axis. So there's the real axis and the imaginary axis. So this is a two-dimensional complex plane. So you can have bit 0 being +1, bit 1 being -1. Or you can have multiple bits for each complex number. So you could have 2 bits and have like a 4-point constellation. So this is called the modulation process, and most of this is baseband processing. It can happen in the digital domain. And then once you have this, what you do is you generate an RF signal. Say if you want to transmit Wi-Fi frequencies at 2.4 gigahertz, you'll generate a 2.4 gig, oops, sorry. Yeah, you'll generate a 2.4 gigahertz oscillator, and then mix it with this stream of complex numbers. And then you'll amplify that and transmit the signal over an antenna. And this second part is called analog front end, and this is the more power consuming part because you have an active component called the amplifier. You want to generate some signal. So for your Wi-Fi, you're transmitting around 100 milliwatts, and that power is what makes communication so power hungry. So clearly, what this means is that generating the RF signal itself is the more power consuming part, but if you just want to modulate this, it's relatively power cheap. So in this space of solutions, like with this understanding, you can approach the solution space. There are two kinds of techniques to reduce this power. One is that you just transmit less data. You could transmit less power and use more complex techniques for decoding on the receiver, or you could just transmit less frequently. You can duty cycle more often. So there's a large space in that domain, which I'm not going to cover in this talk, because most of this, like the session tomorrow is, or actually all of the session tomorrow is related to the second solutions, which is about not generating your own RF signal. So if you can create devices that can get by without generating their own RF signals, you can reduce the power cost of communication by a lot. So let's start by talking about the high-level principle of how that will work. So if you don't want to generate your own RF signal, what is your option? You can reflect. And that's exactly what these devices do. So this is a space of work called Backscatter Networks, and this is how it works on a high level. So let's say you have this tag. Oops, sorry, I keep making a mistake on this. Okay, yeah. So yeah, let's say we have this tag that wants to communicate to this access point. The access point is the one that will generate the signal, and the tag will just reflect the signal back. And by modulating this reflection, so you can, on a very high level, you can think of it as turning it on and off, or you can just change the amplitude of this reflection. You can communicate bits. So if you want to communicate bit 1, you can communicate a high amplitude. If you want to communicate bit 0, you want to communicate a low amplitude. So just by modulating this reflection, you can communicate simple bits of data. So by doing that, you don't have to generate your own RF signal, and that's how that's the whole reason why you want to do backscatter. And one of the simplest examples that's most prevalent is this small tag called RFID tags. I actually have one right here with me. They're very simple small tags. They can work from a distance, typically up to 5 meters. They actually even don't need any power for their baseband processing, that is the digital processing. They can harvest it using RF as well. And one of their main selling points is that they can work in non-line of sight. So unlike barcodes, which require line of sight, close distances, RFID tag can work from a distance. So let's talk about these RFID tags a little bit more. Where would you think of using these RFID tags, right? There's actually a lot of applications. One of the most interesting applications is inventory monitoring. So there are estimates that say that inventory losses amount for about trillions of dollars every year because things get lost, people can't find them when they're required, there are thefts and you don't know there are thefts, so there are like missing demands. So there are all these reasons why you might want to do inventory management frequently, and you could do that by just sticking these tags to all of your objects. They're really cheap, they're a few cents per tag. And then you can do frequently monitoring of your inventory so that you know if something is lost, if something is missing, so on and so forth. There are actually more interesting applications. There are other interesting applications as well. So one of these is very relevant to India. If you've seen like the new toll tax in India, they have the fast tag, which can do automated toll collection. And it exists like in other countries as well. On the east coast of the US, it's called Easy Pass. On the west coast, it's called Fast Track. But the high-level principle is the same. You stick an RFID to your car. As you go through a toll tax, they'll read that RFID, deduct money from your account. So let's move on to the first research theme in this space, which is also going to be covered tomorrow. And the first research theme to think about is medium access. So when you have these really low-power tags, how do they decide who accesses the medium? Let's say I have like hundreds of these tags all around, and I have a reader who transmits its signal. These tags have to decide who's going to communicate when. So in the RFID space, there's a lot of different solutions, and one of the solutions is just to use the EPC Gen 2 protocol, which does some sort of collision avoidance. So it does some time domain duplexing of responses from the RFIDs. But generally, these, like sending any sort of responsibility on the tag is problematic because it costs power. You don't want to give any responsibility to the tag. You want to delegate all the responsibility to the receiver or the reader. And that's the second space, where you want to let tags transmit. They can transmit whatever they want, whenever they want. You'll handle the collisions at the reader. And one example of this is to leverage frequency offsets. This is a work that Umid did in SIGCOMM 2015. And the idea of the work was fairly simple. Because these tags are cheap and really low power, they have very cheap oscillators, and the frequency, the center frequency is not reliable. And you can use that differences in frequencies to separate out the tags in the frequency space. And the other sort of idea, which is more relevant to the paper tomorrow, is this idea of using clusters in the time domain. So on a very high level, let's say I want to send these bits. I want to send bit 1, bit 0, bit 1, bit 0. And they represent two different things on the IQ domain. So there's bit 0 and there's bit 1 in the complex space. What happens if multiple tags collide? So there is one tag which wants to set bit 1 at bit 0, and the other one which wants to send 0, 0, 1, 1. And then they collide, and the collective signal looks something like this. But if you look at it in the complex space, you can get 4 clusters. And each of them corresponds to a different state of the network. So if the two tags are transmitting 0 and 0, you get this cluster on the bottom left. If they're transmitting 1, 1, you get this bottom right, and then you get something in the middle, depending on what these tags are transmitting. So this is a high-level idea of how you would want to identify multiple tags transmitting at the same time. But then the problem is that sometimes these clusters can overlap, because there's no guarantees of how these tags are going to combine. They can combine constructively, destructively. These clusters can be different. These clusters can be close by. And it happens more often when there are more tags colliding. So this is just 2. If they have like 4 tags colliding, you'll have 2 to the 4. And if you have 5 tags colliding, you have like 32 different responses. And those clusters are bound to overlap. So that's exactly the problem that a paper tomorrow is going to deal with. It's called parallel backscatter in the wild. And I'm not going to delve into details as to how they solve it. I'll just give you a very high-level idea, and tomorrow they'll probably describe it in much more detail. So on a high-level idea, the idea is the following, that even if these clusters are together, they appear at different times. When you're transmitting one bit, you'll see more bits coming here. And if you're transmitting the other, like 1, 1, you'll see more signals coming here. And depending on that idea, they can separate these clusters into 2 different zones. So you can have one cluster for 1, 0 and one cluster for 1, 1. And this is a scheme that the authors called super clustering. And in the paper, they showed that this can improve throughput by up to 11.7x. So I'm very excited about this paper tomorrow. But while you think about this paper, when you listen to this talk, think about the following things which are important in such works. One is that what are the inherent assumptions that the authors make about multiple tags transmitting at the same time that enables them to decode parallel transmissions. And the second thing is, what does this ability to decode multiple transmissions at the same time say about spectrum efficiency? Because if ideally, when you want to use your spectrum, you want to be as efficient as possible. You want to send the highest data rate. But in this context, if you can, it seems that you can transmit more, because if 2 tags can transmit at the same time, and if even in that scenario I can decode them accurately, it means you're not using the spectrum efficiently, but that's probably a price you pay for low power networking. And the third thing is that how many tags can this approach scale to? Because as the number of tags grows up, you're going to, again, you'll have clusters that overlap more and more, and then the noise is going to come into play. So with all of those constraints, how many tags can the new approach called parallel backscatter scale to? Okay, so I can also take questions if there are any, or I'll move to the second research theme. Cool, I'll move to the second research theme for tomorrow. The second research theme for tomorrow is related to localization and sensing. So if you can attach these tiny tags to different objects around you, and you can locate them. For example, I can locate my wallet, I can locate keys in my home, you can locate stuff in factories, tools, workers. You can also enable a robot to locate objects around it. So localization for these tags is a really fundamental primitive, and there's a lot of work on that. But most of it was covered already in the topic preview session yesterday. But there's a new research theme which is emerging, which asks the following question: is that can we use these RFID signals to sense the environment instead? And there's this paper called RFID Hacking for Fun and Profit, again tomorrow. And it uses this very simple idea. So I showed you this tag, right? There's this very simple tag. And the idea is the following, that I change the circuit a little bit and put a sensor on it. And that sensor is going to change the reflections. And by understanding those reflections, I can measure those sensor values. So this graph probably shows this better. There's an antenna, like this long thing is the antenna, and there's a small chip that does the modulation. And what this paper shows is that I'm going to make a cut just right next to the chip and put a small sensor component there. It can be a photodiode for measuring light intensity. It can be a temperature sensor. It can be a touch-based button. And what happens is that if the sensor values change, so let's say you're originally getting bit 0 and bit 1 in those two clusters. If the sensor values change, you're going to make those clusters move away. And based on the change in the reception of individual bits, you can infer what the sensor value is. And they have a really cool demo in the paper where they design a battery-free keyboard. So depending on which RFID you're touching, they can detect the touch and detect the key press. So they're using 4 different key presses, A, B, C, and D. So when you read that paper, I still have questions that you should think about. One of the questions is that what are all the things that such systems can sense? Not all systems can do passive sensing. For example, if you want to sense something like pH, can you sense pH? Can you sense moisture? Or can you just sense temperature? What is the limitation on the number of things that can be sensed with this approach? The second question is how minute can those variations be? Can I sense temperature variations of 1 degree Celsius and 2 degrees Celsius, or 1 degree Celsius and 10 degrees Celsius? And a lot of it depends on the SNR that you're receiving, the signal that you're transmitting. And finally, what will be the cool extensions that we can build using this system? Because this system, on a very high level, is a very cool idea, very nice. So we want to discuss what are our own applications that we can build that will be completely passive and battery-free. So I'm pretty much done with the RFID overview. The good thing about RFIDs is that they're 0 power stickers. The bad thing about RFIDs is that you need extra hardware to read them. You need an RFID reader, which does not exist in this room, for example. So how can we get around that? And the answer to that is this research space called Wi-Fi Backscatter. So the objective of Wi-Fi Backscatter is very simple. It wants to design backscatter devices that can communicate with off-the-shelf devices. So essentially, I want to design an RFID tag that I can read with my cell phone, and without needing an extra RFID reader in the environment. And there's a long line of work starting about 5 years ago with different universities, different authors doing different kinds of work. This is Wi-Fi Backscatter, Hitchhike, Freerider, Passive Wi-Fi, FS Backscatter, so on and so forth. So there's a lot of work in this space. And I'm going to discuss what are the high-level ideas that make this space interesting and challenging. So let's say we want to make the cell phone communicate with this access point but battery free. So what do we want to happen? So this guy is going to communicate a signal back, and there's going to be a reflection. But the problem is, so the problem is that this reflection is going to be much smaller than the signal that this AP is transmitting anyway. And this is something called self-interference, that the AP is interfering with itself. So one line of work deals with canceling this interference on its own, but that requires additional hardware, so I'm not going to discuss that. But there's a different line of work, and what it tries to do is to move these reflections to a different frequency than the original signal. So what they do is that the tag itself has a small battery that can generate a 20 megahertz clock, and it will mix it with the incoming reflection. And the whole idea is that generating a 20 megahertz clock is much cheaper than, because this guy is just running an oscillator, it does not need a power amplifier. And the amplifier is the power consuming part. So by doing that, what you can do is, so let's say originally you had a Wi-Fi signal that was very high and a small backscatter signal, and they were colliding on the same frequency band. The x-axis is frequency, the y-axis is amplitude. So by mixing it with the 20 megahertz signal, you can move the backscatter signal to an adjacent frequency band, and now you can have two devices. So one device is transmitting the original signal, and another Wi-Fi access point is reading the backscattered signal. Okay, so this is how it works on high level. There's a backscatter signal on one AP, there's the original signal on the other AP. And then you can decode these signals based on that. So now, there's the other question. If I want my cell phone to read these backscattered signals, I want them to make sense in the Wi-Fi world. I cannot have arbitrary signals coming in, and I don't expect my Wi-Fi chip to decode those signals. We want a well-formed packet at the receiver. Recall that transmission has complex symbols. So if you just don't transmit random bits. So if you're transmitting bits, you probably can turn them on and off, as RFID does, but this is a more complex scenario. And one of the simplest ideas in this space is to do a packet level reflection. So you can either reflect a packet or not reflect a packet, and that itself communicates a bit. So if you don't reflect a packet, that communicates bit 0. If you reflect a packet, that communicates bit 1. So if you want to communicate 1, 0, 0, 1, 0, 1, you eliminate some packets in your reflection. So the good thing about this is really easy to implement, really simple. The bad thing is it's low data rate, because if you even send like 1 packet per millisecond, you probably get like 1 kbps at best. Okay, so can we do better than that? And the idea that some of these papers have proposed is that you can do symbol level transitions. So recall that there's a sequence of complex symbols that we are transmitting, and these complex symbols have different representations. So let's say I want to transmit symbol 0, 0, or this is the original transmitted symbol. And by changing the shape of the symbol, I can see what the backscatter signal is. So the backscatter signal, what it will do is it will change the phase of this transmitted signal, and move this from 0, 0 to this location 1, 1. And you can do like arbitrary phase shifts. I'm using 180 degrees here for an example. And by either changing the phase or not changing the phase, you can communicate bit 1 or bit 0. Cool. So there are several open research questions in this space, because this is relatively new. And I'm listing some of them here. One of the questions is that you're still using an extra Wi-Fi channel. It causes interference for other devices. The reason we have multiple Wi-Fi channels is I want my Wi-Fi to operate while my neighbor is operating at a different channel. But now if I use a different channel for my in-home devices, it's going to interfere with my neighbor's channel. The second critique of this work is that you still need an additional device. Like you need 2 access points as opposed to 1. So it is fine for a conference room like this, because we'll probably have multiple access points lying around. But for a smart home kind of setting, you typically have 1 access point, you don't have 2. And if you're going to put a different device anyway, why won't you just do RFIDs, which are probably like more low power than this network? The other critique, which is sort of hidden and not as prominent, is that in most of these works, there are 3 distances that come into play. There's a transmitter to tag, tag to receiver. And the transmitter to tag distance is relatively small, less than 1 meter, because you want to have a large power to harvest it. And there are still a lot of questions on robustness, which I'll discuss in detail in the next few slides. And the other question is, what happens when multiple parallel tags are transmitting at the same time? Like, how do you do collision avoidance? How do you do, like, what kind of MACs do you design? These are similar to the questions for RFIDs, except that RFIDs are in a more mature stage, and this technology is relatively nascent. OK, so let's discuss the challenge of robustness. And the reason I want to discuss this in more detail is that there's a paper tomorrow about this. And the idea, that the problem that the paper is trying to solve is the following. So we rely on the distance, a signal to go from the transmitter to the tag to the receiver. But what if the transmitter to the tag link is weak? And that can happen very often in indoor environments because there's multipath. You don't really know where the tag and transmitter are in the real scenario. So what can you do in that case? And the solution that the paper proposes is fairly interesting. So what it does is that it does a relay through different tags. So in a smart home or in a smart farm or in a smart oil field, you're probably going to have multiple sensors lying around, and some of them are going to see a good signal and some of them are not going to have a good signal. So if you can use the tags that have good signal to relay information across different tags, then you can probably get around this problem. So the paper tomorrow deals with only 2-hop networks. It's not really multi-hop. But I'm assuming there are extensions that can be done for an n-hop network. Okay, so the first thing, this is again going back to what we said, that if you're doing one hop, if you're doing a direct backscatter, what you do is you shift your backscatter signal to a different channel. But if you're doing multiple hops, so if you have multiple tags communicating, what do you do? And in this paper, the authors make a design decision where they shift the backscatter signal by one more channel. So you have the Wi-Fi signal, and then you have, and then you have two channels. So for each hop, you have a different channel. But what the authors are doing is that they're only using the third channel for reception. And there are some clever ideas in the paper, and I'm sure they'll discuss that in the talk. And the second channel is just used as a relay. And the paper shows that they can use this technology to improve throughput by 10x in indoor environments with obstacles. So the key to note here is that this is an indoor environment with obstacles. If it's a flat environment, if you don't have blockage, probably you don't need multi-hop. So when you listen to this talk, I think there's several points to think about. One of them is that Extandum, so this is a paper called Extandum. It describes 2-hop networks, and it will be interesting to think about what are the challenges that exist for extending to a generic n-hop network where n is greater than 2. How do they decode 2 signals from one backscatter receiver? So they discuss this in the paper. And then we want to think about what happens when there's only one tag. So you design these tags. Do they assume that there are multiple tags? Do they not assume there are multiple tags? What sort of protocol inventions exist in that space? And finally, there's this always this question about this line of Wi-Fi backscatter work, is that what are the distances between different devices? Is it like the tag to transmitter distance, transmitter to tag 1, tag 2? Like, what are all those distances? How do they come into play? What sort of SNR are you expecting? Cool. So now I move to the last part of this talk, which is about human body backscatter. Of course, I can also take questions. If you have questions, just raise your hand, and I'll be happy to answer them. Yeah, so there's this new line of work. Actually, this is relatively recent. Maybe like, actually, some of it is not recent, but this is mostly based on the framework of radar, that when you send signals, human body also reflects them back. And a small portion of that signal goes inside the human body. So the question that this line of research tries to answer is that what can we do with the reflected signal? And what can we do with the signal that goes inside the body? So these are the high-level 2 questions that we're going to try to answer. So the signal that's reflected back, it changes when human body is breathing or human body is moving. And people have tried to use that for different kinds of applications. They have tried to use it for locating people without having them carry devices, for monitoring their breathing, monitoring their heart rate, even emotions, for example. So this is the line of work that the paper tomorrow deals with. And yeah, OK. So there are multiple methods to measure the signal change. You either measure the change in amplitude or the phase, or you use like wideband signals, you use narrowband signals. There's several design decisions to make. And the question is that how do we understand how these design decisions impact the actual accuracy of the system? Because the evaluations for these papers are typically done in different environments, and the environment has a big role to play in evaluating the systems. So the paper tomorrow is an experience paper, and they want to do a performance study of multiple techniques, and they compare 4 different methods. One of them is based on RSSI, one of them is based on CSI, and the other 2 are based on channel impulse response on like wideband signals. So the key questions that this paper actually teaches us is how do you set up performance studies when you want to do a fair comparison between multiple different technologies? Because it's really hard. You don't want to be unfair to some of these technologies that you're comparing against. So the paper makes some interesting design decisions, really interesting. So I'm sure I look forward to those, and I'll encourage you to try to like look into those aspects of the talk. Also, what environmental issues exist for good reporting of respiration rate? So multipath is one. Can human motion? So if you move, the breathing signal becomes much weaker than the motion signal. So how do you deal with that? And what are the are the errors correlated across mechanisms? If you're used, for example, can you use 2 different mechanisms together to improve the accuracies? Because if the errors are uncorrelated, then you can do that. If the errors are correlated, then it becomes much harder. So the paper has some interesting insights in that as well. Cool. So now let's talk about the signal that went inside the body. So there are small amounts of signal that can penetrate the human body and go inside. And the question is, can we use this small amount of signal that goes inside to enable in-body backscatter? Because there's going to be a lot of, in modern medicine actually, there are going to be a lot of devices that rely on low-power networking. And one of those devices is something called a capsule endoscope. So if, like 5 years ago, if you wanted to do an endoscopy, you have to take a long tube, thrust it through your mouth, it has to go through your body, take pictures. But today, you can do it with really small, tiny capsules that have cameras on them. But these cameras need to communicate data. They need to be localized inside the body, and that's a perfect setting for doing in-body backscatter. And the other application that I find particularly interesting is something called cancer radiation therapy. So in cancer treatment, there is a phase called radiation therapy, and in that phase, you deliver a high dose of radiation to tumor cells in your body so that they die. But what invariably happens is that these tumors can be located in moving areas of your body, for example, the breasts or the lungs, which move when you breathe. And as a result, the beam can miss the tumor cells and hit healthy tissues around it. And that can be problematic if those healthy tissues turn out to be lungs or heart, which are very, very sensitive tissues. So what doctors want to do today is they want to put in small implants inside these tumors so that they can track them. But again, you want to track these signals using radio waves, you have to get the signal out from them, and then you have to locate them using different technologies. Yeah. So, and then the main challenge of this line of work is the following. So this signal that's reflected off the human body is much, much stronger than the signal that goes inside. And the reason is that, first of all, the signal that goes inside is very small, and it's exponentially attenuated because of the electrical permittivity of the human body. And as a result, the signal that gets back after backscatter is about 100 million to 1 billion times stronger than the target signal that we are trying to get. So there is actually a bunch of papers recently in this space, and all of those papers try to have a similar setup. This is a setup from my paper in SIGCOMM this year, but there's also like other papers in this space. And the setup is like you work with animals, you try to put small tissues, and you try to get a signal outside. And the state of the art in this space is that you can get about 1 megabits per second throughput in this in body, and you can get centimeter level localization. And both of them are good steps, but they are not. They don't meet the requirements for applications. For example, for tumor tracking, you would need millimeter scale accuracy, which is not there yet in this space. So with this, I'll conclude the talk. I'll summarize the research theme that I discussed today. So first of all, I discussed that you want to delegate the responsibility of medium access from these small low-power tags to readers or other devices that have access to power. Yeah, so the second research team in this space deals with localization and sensing using low-power devices. And then there is the question of how can we make these low-power devices communicate with off-the-shelf devices like our cell phones and Wi-Fi access points. And finally, I discussed human body backscatter. That is what happens when human body reflects and devices inside the human body reflect. With that, I think I'll conclude my talk and I'll take questions. Thank you.